Hi, so my name is Prem and today I'm going to talk about, as sir said, about approximate thermal state of a quantum system. So I would like to thank Adam Stratton and Professor Sivasis Ghosh for helping with different aspects of this work, and recently it came in archive. So the question is, what is the problem? Many of you might be aware that the thermal state of a quantum system at inverse temperature beta, it is given as e to power minus beta of the Hamiltonian h, where this p square is the p is the momentum operator, p square by 2m is the kinetic term, plus Vx is the potential term. So the thermal state is just given by e to power minus beta of the Hamiltonian. But this is only true if the system is weakly interacting with its environment. The general thermal state can deviate from this state, and we know how to calculate that general state, but it's computationally very expensive, and general analytical expression for it is unknown. Its result for some limit is known actually. Recently in 2020, this PRL came, which says that in infinite coupling limit, the thermal state is given as e to power exponential of minus beta Vx. So the potential term is missing. Only Vx is there. So this result was there. So we are interested in finding out whether can we find the given analytical expression for this thermal state in maybe more generalize this. To get into this, let me introduce you to path integral approach to quantum mechanics. So it's one of the simplest ways to introduce quantum mechanics to someone. The idea is that if you want to know what is the probability for a particle to go from one position to other position in some time, so what you do is you sum over the contribution of all the paths that the particle could have taken in that time. Each path will contribute something. In the end, you add all of this together, and this will give you the resulting contribution of the resulting probability of this transition to happen. So for open quantum system, same path integral gets slightly modified. It doesn't get modified, but the expression is given in this textbook, 30-year-old classic textbook. So basically the idea is that it looks complicated, but let me explain it to you. This let q tau be one of the paths that the particle could have taken. So sq tau is just a number, which let's forget how we will calculate for now, but let's say we have a computer program which can do it for us. So sq tau is just a number. What you do is you put it inside an exponential with a minus sign, e to the power minus sq tau, and this gives you the contribution of that path. And then you add over all the paths with their corresponding sq tau, and the sum end result gives you the final probability for that thing to happen. Okay, so let me get into the expression for sq tau. So it has basically three terms. The first and second term, some people who have studied path integral may be familiar with this first and second term. First term is just the kinetic term. Q tau by dq by d tau is the velocity. So it's velocity square, mv square by 2. And the second term is a potential term plus vq. So the third term is coming because of the path, because of the environment. And this is, let's forget what the expression for k tau minus tau prime is, but this is how it is. I'll not go in more detail. It's there in this textbook, but it's not required for our requirement. Okay, so the thing is, can we see this? So these people in this PRL, these people arrived at this result using perturbation theory. So the question is, can we see this directly from this equation, this infinite coupling result? The answer is yes, because this expression k, it's because of the environment. So if environment is not there, this k will be 0 and this third term will not be there. On the other hand, if the environment is there, strongly present there, then this factor k will be infinitely large. So this sq tau, so if for a path, if q tau minus q tau prime, tau and tau prime are at two different times. So if q tau minus q tau prime is positive or is non-zero, the square will be positive. It will multiply to a very large number, and this sq tau will become a very large number. When it goes inside an exponential with a minus sign, it becomes a very small number. So what this means is, for any path, if q tau and q tau prime are not the same, then that path will not contribute. So the only path that will contribute will look something like this, straight path, where q tau is q tau is equal to q tau prime for all tau prime, tau and tau prime. So the only straight path contributes in the large coupling limit. This would mean that the third term will not contribute at all for the paths which are contributing, because it will be large number multiplied by 0. And the first term will also not contribute because dq tau of, because it's a straight path, this will also be 0. So kinetic term will also go, this dissipative path term will also go. The only term which will remain is this potential Vq. So this integral will become very trivial, and you will directly get this equation. I am not sure whether this argument is clear, but I mean, if you think about this, you will get that it becomes trivial in the infinite coupling limit. And we can directly see this result, ultra strong coupling result, coming directly from the path integral approach. So the question is, now that we have this intuitive way of looking at it, can we do better than this ultra strong coupling result? The answer is, I mean, if the coupling is infinite, then only one path contributes. If the coupling is not infinite, then only nearby paths will contribute. So we don't have to look for all the paths in the path integral, only nearby paths. And also, it turns out in the same textbook, the result, if the system was a harmonic oscillator, which is just a quadratic potential, if result was harmonic oscillator, the answer is analytically known. So if not, if the paths which are contributing have only like small, only have small variation, then you can locally approximate that potential as a harmonic oscillator. So what you basically do, you have, let's say, a complicated potential. Everywhere you fit a harmonic oscillator, and you know the answer for harmonic oscillator. So you just cut and paste the answer there, and you get an analytical solution for the thermal state of that system. It will have some error, of course, but there will be some limits in which this result will be quite accurate. The limits are, of course, in high coupling limit where this k diverges. Another limit is if Vq, the potential, is changing very slowly. So everywhere this harmonic approximation is quite a good approximation. No matter what be the distance on which the path integral is exploring the space, your harmonic approximation is doing a good job. So these are the two limits in which this approximation will work quite well. Okay, all well and good, but there is one problem. What about this inverted harmonic oscillator, this orange curve? So we are using analytically known solution for an inverted harmonic oscillator to solve this problem. Will it even make sense, because the e to power minus beta h of an inverted harmonic oscillator is undefined? The answer is we can do that. The reason is it's undefined for some harmonic oscillator. If the imaginary frequency of this harmonic oscillator is not too large, it turns out the state is undefined, but the local path integrals are still defined. The reason for this is this. The potential is inverted. The potential is inverted. So paths which have large deviation from this potential will tend to contribute more. But then in the path integral there are two terms, kinetic and dissipative terms, which will prevent the large deviation, paths with large deviation. This first term, kinetic and dissipative term, they will prevent the large paths with large deviation to contribute more. So this kinetic and dissipative term versus this potential term, they have some kind of competition, and it turns out that the potential term only wins if its frequency is larger than some limit. So this approximation can work with, by using, you can actually use a result for an inverted harmonic oscillator for this approximation as well. Okay, so these are the two limits in which this will work. Okay, and then I'll give you another limit in which this method will work exactly. So we talked about this dissipative term and this potential term. This dissipative terms in large coupling limit, it gives you exact result. This potential term also gives you a limit in which if your potential is changing slowly, then it will give you exact result. The first term also gives you a limit. That is a high temperature limit. In high temperature limit, the first term starts dominating, and any path which has any variation, that path will not contribute. The reason for this is like this. In this beta is inverse temperature. So in high temperature limit, beta goes to 0. So let's say I want to go from this part of the stage to that part and come back in 20 seconds. Then I'll need some energy to do that. But if I have to do the same thing in 1 second, or let's say 0.1 second, then I have to expend a lot of kinetic energy. This is the reason why the kinetic term dominates, and again the again the thermal state is given as e to power minus beta b. To summarize, this approximation works well in large coupling limit if potential is varying slowly, or if in the high temperature limit, or a mixture of these three. So, okay, thank you.
Thanks, Prem, for this very nice talk and questions.
In the potential, you didn't fit the minima actually, but you fit it. So usually what you do, you fit the minima only.
No. I am fitting at every point. This is just for illustration. At every point of this potential,
okay.
I am putting a harmonic oscillator and using the answer for answer for harmonic oscillator at that point.
Okay. So this is only one of the possible.
Yeah, just for illustration.
Oh, okay. Thanks.
Any more questions?
For example, in the inverted harmonic oscillator case, you said you know the analytical solution.
Yes.
So can we do this for some cases when we don't know the analytical solutions or the potentials are not analytically solvable?
I mean, for harmonic oscillator, we know the analytical solution. We are using that to solve for unknown potential. But I didn't get your question.
In some of the cases, for example, in the inverted harmonic oscillator, when the path integral might not work that nicely.
So that's the thing. If we know how to solve the path integral even for inverted harmonic oscillator, if the imaginary frequency is not larger than some threshold. If it's larger than that threshold, it diverges. But for some inverted potential, again we can do the calculation. The thing is, if your potential has this sharp, if second derivative is very sharp, then for given coupling or temperature, it might not work. But again, in the infinite coupling or temperature limit, again the number of paths required are very small, and again this kicks in. So again this method in that limit is again applicable, because e to power minus beta Vx, what they arrived in this PRL, this is valid for any potential. So in the infinite coupling limit, it's always, even if it's any harmonic potential, it will work. I mean, if the potential itself, the actual potential is bounded, as long as it's bounded, this black curve, as long as this one is bounded, the harmonic approximation itself will work. So actually, okay, I don't know whether I answered your question.
Yeah, we can talk later. Thank you.
Okay.
Thanks, Prem. And we end the first session by thanking all the speakers.